Hey everyone, welcome back to my channel EduVibe. In today's lesson, we are moving to the next topic of the atomic physics, which is the fission and fusion. That topics are very easy topics, and we are again doing some radioactive decay thing. But we're not like actually making the reactions now. We are just doing some calculations, some big calculations in that. So when a nucleus has activity is greater than 120, it will split into two nuclei to achieve a greater stability. That is the higher binding energy per nucleon. So when it is like A is greater than 120, they will split into two nuclei, and to achieve a greater stability, this is called like a higher binding energy per nucleon. This is known as the fission. When this thing happens, when they are split into two nuclei to achieve the greater stability, is called the fusion. And the energy produced will be the difference in the binding energy of the original nucleus and the total binding energy of the products. So the nucleus original thing and the binding energy total thing of the products are the difference of that, so the energy can produce. The two low mass nuclei combine to form a single nucleus with the A, which is activity, is less than 60. The resulting nucleus is more tightly bound, which is known as the fusion in that case. So when there are two low masses, they are combined to make the single nucleus is less than 60s. So resulting in the nucleus is tightly bound. So it's called the fusion. The reaction gives off energy equal to the difference between the total binding energy of the original nuclei and the binding energy of the product. Again, there is a some difference between the binding energy of the original nuclei and the binding energy of the product. The saw earlier that calculated energy is fusion equation or the fusion equation. Einstein equation for the mass energy equivalence can be used in that, which is the energy times delta def, the mass def, and the c square. And this thing we can use this thing now, which involves the nucleons and the nucleus. Now this is basically the reactance thing, and this is basically the product. So we use the same two formulas like this. These are the reactants and products, and we use that formulas. And from here we have the final physics principle number 6, which is conservation of the mass and energy. And this will be our final physics principle number 6. Now we have to know about that. So let's do fission fusion separately, and we have some things to know in both. So firstly, we have a nuclear fission. It arises from a free neutron colliding with a large nucleus. The nucleus will absorb this neutron, which ends up forming a highly unstable isotope that breaks up almost instantaneously. So we have this. The greater nucleus, large nucleus, colliding with the neutron will give you some things with the neutron. So they are the unstable isotopes. These are the unstable isotope, these and these, and they produce as the product. The daughter elements produce will the lighter nucleus than the parent element, as well as neutrons. Neutrons will be released. So you can see the three neutrons will be released, and which themselves can be absorbed by the other elements and continue the fission process. This continues the fusion process and they absorbed by the other elements. This is known as a chain reaction. This is the type of a reaction which is a chain one. So after that three neutrons, they go with another some large element, then they again made some three neutron, then again that do this same thing with that chain one. This is important for in the nuclear power. So nuclear power, a typical fusion reaction of uranium-235 is driven by this. So it's the uranium-235 reaction of the nuclear power. So that reaction is very important. You have to know this. And one thing, an important thing in both the one line is this thing. We also do that line in the fission too. So the fusion too. So the fission releases more energy per reaction in comparison to the fusion. So the fission has a more energy per reaction. This is the key word in this. There is a more reaction per reaction, more energy per reaction in comparison to the fusion. In the fusion case, we have some per kilogram reaction energy can be used. So this thing shows a diagram for the fusion process. Then we have some advantages and disadvantages. Advantages is that easy to trigger. Fusion is easy to trigger, needs only the low energy neutrons. This has a higher energy yield than coil and have a 2 million times more. Disadvantages, this has the more radioactive waste, expensive, this is costly to environment, and have a non-renewable resources in that. So we have example of the fusion, and this is like the big examples we're dealing with in that. And one thing that you have to find that which is the fusion reaction, which is the fusion reaction. So the example says a uranium 235 nucleus absorbs a neutron and then splits into the bromine 87, lithium 146, and additional neutrons. Determine the balanced. This determine the balance equation for this reaction and determine the energy released in MeV. You will need the following nuclear masses. So these are the nuclear masses of these all things. And how to balance this? So balance means you have to like find this X in that. How can find it X? You know the number of nucleons on the both sides should be equal. Here we have 235 plus 1, which is 236. Here we have 87 plus 147 or 146, which will give you 233 and plus X. So plus X means we have 1 and we have only one thing. So basically we need 3 times more. So 3 more to balance this. So this means the X is 3 in that case. This one is 3. You have to show this. So for the A, which is the upper thing, number of nucleons. So 235 plus 1 is equal to 87 plus 146 plus X. 236 is equal to 233 plus X. You will get X is equal to 3 when you minus this. Same, you have to check the Z2, which is 92 plus 0 is 35 plus 57 plus 0. When you solve this, you get 92 is equal to 92. So that's the balance thing, and that 3 you have to add in this. Now, you have to find the energy in the MeV. For energy, you want the E you want because you have C, so you know that E is equal to delta M and C square. You want this to find this. In MeV and C square you have. Okay, you know delta M is equal to the mass of the reactants minus the mass of the products. You know this thing? So what are the reactions? Reactants we have mass of the uranium plus the mass of the neutron minus in the products we have the mass of the bromine plus the mass of the lithium plus we have a 3 masses of the neutron 3 times. So we add all things of the products of these two and with included the uranium and the neutron, and then we do the all the products added. With that, make sure the neutron have the 3 neutrons. We have multiplied this by 3 in the product side. So these things we have, and you have to put the things down. You have all masses and that your answer. So the mass of the uranium is 235.043930 U plus the mass of the neutron is 1.8008665 U minus the mass of the vanadium is 86.9207111 U plus the mass of the lithium is 145.92579. This is 791 U plus 3 times 1.008665 U, the mass of the neutron. When you solve this big thing, you will get 0.180098 U. Make sure you have checked your values when you put it in calculator because there's a big one and you have to be careful with this. Now for calculating the energy, you want this in kgs. So multiply this by 1.66 into 10 raised to power minus 27 kgs upon 1 U. When you solve this, you get about 2.9896 into 10 raised to power minus 28 kgs. And this is the fat mass, and E is equal to the fat mass C square, You have to put this thing 2.9896 into 10 raised to power minus 28 kgs multiplied by 3.010 raised to power 8 meter per second square. When you find this, you get about 2.6906 into 10 raised to power minus 19 joules. But you want this in MeV. So first recommendation is EV. So EV, you have to divide this by 1.69 raised to power minus 19 joules. Joules cancel. Now want in MeV. So 1 MeV is equal to the 10 raised to power 6 EV. So EV also cancel. When you solve this, you get a 168.166 MeV. Basically, you get 168.167 MeV. These are 6 digits, and you get this. This is your energy for that. That's how you can find. So, the long one, but the easy things. You have to just for development, you have just add all the reactants, add all the products, minus them, get defined mass in kgs, and then do this. So this is very long question, but easy thing you have to do. Make sure the values are correct. Now we have a fusion. So in the fusion, what powers the sun? Was a question that the scientists for many years. When the nucleus was discovered by the Rutherford along the scientist's mass energy equivalence, the key to answering this question was determined. It was determined in the 1920s that the sun was composed of primarily of hydrogen, which is approximately 73%, and helium 27%. And then this scientist noticed that the four hydrogen atoms of the protons have about 0.8% of more than the mass of helium nucleus, and thus this might be very well mechanism for powering the stars. This whole thing happening, and this is the behind story. Then we can see that fusion is the process of combining small nuclei together to make the larger nucleus. Some small nuclei combining the all and that the larger nucleus, which is called the fusion. And the main key point in that to like recognize that which is the fission and which is the fusion, that these reactions are occur naturally in the sun. So these are the sun. When you mention the sun thing, so it powers the sun when it naturally occurs with the sun. So these things have to happen in this. And again, the another point which I said you in the fusion, you have to be careful in the fusion too, that the fusion releases more energy per kilogram of fuel in the presence of the fusion. So again, this point, more energy per kilogram, in that the fusion releases the more energy per reaction. This is the per kilogram of fuel in the presence of fusion. So you have to take care of this thing, this line too, in that thing too. Advantages in this, we have advantage that there is abundant fuel and this is stable by the products. Byproducts are very stable. In the fusion, the byproducts, the products are very unstable. Disadvantages, they have a high temperatures, which about a 10 to raise to power 8 Kelvin are required to overcome the repulsion of the nuclei. So they have very high temperature. That's why this is a disadvantage for them. So we have example for that, which is the same thing we take care in this too, that we do something the same things we for doing that too. So determine the energy released by the photon along with the wavelength in the following fusion reaction, the part of the process that powers the sun in the proton-proton chain. We have this reaction over there. You will need the nuclear masses, helium-3, helium-4 and hydrogen-1. So you want the energy of the photon and then you have a wavelength. So the same process you can follow. The effect mass is equal to the mass of the reactants minus the mass of the products. So what you have as in reactants, we have a helium-3. So 2 helium-3, because 1 and 2, these are the 2, both are same, minus, then at the other side we have a 4 helium mass plus the 2 times the mass of the hydrogen-1. You have these things and you can put the things now. So 3.016029 U minus 4 helium, we have 4.002603 U plus 2 times 1.007825 U. When you find this, you get the Fat mass of 0.013805 U. Again, you want in kgs, so 1.6 into 10 raised to power minus 27 kgs divided by 1 U and U cancel out. You will get your defect mass about 2.29163 into 10 raised to power minus 29 kgs. So you do the same thing in that too, in that defect mass. Now you want energy of photon, which is that defect mass c square. You have 2.29163 into 10 raised to power minus 29 kgs. 3.00 10 raised to power 8 meter per second square of that. When you find this, you get about 2.02467 into 10 raised to power minus 12 joules. They didn't mention you want in specific units, so you stay in the joules and leave the answer like that. Also, they want the wavelength. So from this, we can easily find the wavelength. We got this is equal to the hc upon wavelength, and the wavelength is equal to hc upon the energy of the photon. You know the h, you can use the joules thing, 6.6 10 raised to minus 34 joules per second, says 3.0 10 raised to power 8 meter per second. Divide this by the energy you already find, 2.062467 into 10 raised to power minus 12 joules. Is it joules? So when you calculate this out, you get 9.6438 something to 10 raised to minus 14 meters. So this is like 5 centimeters, and that's your answer for that. And this is your energy. So very easy questions. You have to just find the defect mass like this formula. You have to know this formula, and basically they are talking about always talking about the energy. Sometimes they want the wavelength too, so find by the Planck's constant. So that's all. You have to do conversions are very important if they mention. So do that conversions too. Sometimes the long questions they didn't ask for the conversion, but sometimes they ask. And the one thing in that why are not using the gamma thing, the gamma in this, because the mass of the gamma is 0 in that case. This always becomes 0, so you can't use in the mass, which is those two 0. So that's all you have to do in the fission and fusion. These are very important important topics too, and very easy topics too. Just have to identify which is the fission quotient, which is the fusion quotient. So that's all for this lesson. Let me see where do I learn smart, not harder. Please like and subscribe to my channel. If you have any questions, let me know in the comment section. See you in the next lesson. Till I get it with EduVibe.